Welcome to Exploring Computing. Today's video is Computer Theory, Analysis of Algorithms. So choosing the right algorithm can make a big difference when you're programming. And in fact, it can make the difference between having a program that runs in a reasonable amount of time and a program that takes too long to run for reasonable sized data sets. So for small data sets, there's a lot of different algorithms that will work, but when you start working with large amounts of data, more and more the particular algorithm that you're using is going to make a huge difference in whether or not you're actually able to analyze the data in a reasonable amount of time, or it's just going to take long enough that for all practical purposes, you can't do it. In this lecture, we're going to start by taking a look at how to look for an item in a collection. And we'll compare some different ways of doing this. And then after we've done that, we're going to take a little bit of a look at how computer scientists go about comparing different algorithms from a theoretical standpoint. All right, so here I've got a list of different sovereigns of England. And the simplest way I can go about trying to find out whether or not a particular name is on the list is using something called a linear search. In a linear search, we're going to start off with the first item, and then we would go through each of the different items one at a time in order. So suppose we're looking for the name Henry. We would start off with Mary. Say, hey, is Mary Henry? No, it's not. Then we go down to the next item and say, is Anne Henry? No, it's not the item we're looking for. Is George Henry? No, it's not the item we're looking for. Is Henry Henry? Oh, yeah, that's the item we're looking for. Therefore, the item is in our list. Now, if we're looking for a name that's not actually on the list, we start off again by comparing to Mary. We compare to Anne. We compare to George. We go through all the way through the list. We get to William. We still haven't found the name on the list because the name is not on the list. And then we realize we're at the end of the list. And so we conclude because we've gone all the way through the list and we haven't found a particular item, therefore, this item is not on the list at all. So one thing to be thinking about here is how long does it take to find a particular item on the list? So suppose we're looking for Elizabeth. You can see like Elizabeth is somewhere in the middle of the list. Suppose we're looking for Mary. Mary's at the start of the list, so we can find her pretty quick. Suppose we're looking for Melanie. Melanie's not on the list, so we need to go all the way through the list. So basically, we can consider a number of different situations when we're talking about how fast an algorithm will run. We can think about what's the best case. So in case of linear search, the best case is, well, it's the first item on the list. It's very, very quick to determine if Mary is on this list. We just look at the first item. It's Mary. We're done. What's the worst case? Well, the worst case is, in this particular algorithm, is the item is not on the list at all. And that means we need to compare all the different items. And then we finally get to the end and we're like, yeah, we checked everything. It's not on here. And then we've got the average case. Generally, when we're talking about algorithm analysis, we're concerned with what happens for large numbers of items. As I mentioned earlier, if you've got a small number of items, you can have a pretty poorly thought out algorithm and still get it to work. It's not very efficient, but as long as the numbers are pretty small, it will still work. It's when you start getting larger and larger numbers of items that it really becomes a problem. So suppose if I've got a list of 1,000 items, it takes an average of 1 minute to find an item on the list. How long would it take on average to find an item if we double the list size to 2,000? Well, I mean, I think this is pretty clear. If we double the size of the list from 1,000 to 2,000, we will double the amount of time on average it's going to take. So instead of taking 1 minute, on average, it will take 2 minutes. And in fact, we can write a little formula that looks like this. Average time to find an item is equal to the number of items divided by 1,000 times 1 minute. But it turns out that our little formula here is highly dependent upon the specific computer, because if I have a faster computer, I can find an item on average faster than 1 minute for 1,000 items. And so really, if we want a more general formula, we would actually write it like this. We would say average time to find is equal to constant times the number of items, where that constant is going to vary depending upon the particular type of computer. but I still know that this general formula where I have some given constant determined by the speed of the computer times the number of items. So as the number of items increases, the amount of time it's going to take me will also increase at a constant rate. Okay, so can we do a search that is faster than linear search? Yes. If the list is ordered, we can do what's called a binary search. How does a binary search work? In a binary search, what we're going to do is we're going to take the list and we're going to divide it in half. And we will determine if the item that we're looking for is in the upper half of the list or in the lower half of the list. And this is similar to, this analogy is getting old, but I have previously asked students and they continue to tell me they do understand this analogy, so I'm going to continue using it. So the analogy would be similar to if you have a physical telephone book and you're trying to find a name in that phone book. You split the phone book in half and you say, is the name in the first half of the phone book or is it in the last half of the phone book? Oh, it's in the first half of the phone book. Okay, I'm going to split that half of the phone book in half. So I'm looking at now looking at quarter sections. Is it in the first quarter or is it in the second quarter? Oh, it's in the first quarter. I'm going to split that in half and look at an eighth versus an eighth and so on. This is the same way you would also look for a word in a dictionary if you actually had a physical dictionary. So let's look at how this might work for our monarchs of England. I've reordered the list because, again, binary search requires that the items are ordered. Okay, so suppose we're looking for Edward. What we're going to do is we're going to split the list in half. Now, it turns out in some cases, we can't split the list evenly in half. And so in this case, I'm going to split the list in half and start with Henry. I'm going to compare Edward to Henry and see if, maybe I split the list in half. This is like, I open up the telephone book and it happens to be that the item I'm looking for is actually right there. I split it in half and there's the name I'm looking for that happens to just exactly be on that page. So it is possible to split the list in half and actually the halfway point, that's the name we're looking for. But in this case, it's not. And so what I can do here is I can say, does the name Edward, if it were actually on this list, does that come before Henry or after Henry? And in this case, since the list is alphabetized, I know that E comes before H, and therefore I toss out all the items from Henry onwards. I'm not interested in those. And I know that if Edward is on the list, it needs to be somewhere in the first half of the list. So somewhere between Anne and George. So I go ahead and toss those items out. And then I split the list in half again. And again, this list does not split evenly. So you need to have some sort of rule in terms of, if the list doesn't split evenly, are you going to go slightly lower? You're going to go slightly higher. So I'm going to go slightly higher and say, we're going to go ahead and look at Elizabeth. Is Edward Elizabeth? No, it's not. If Edward were on the list, would he become above Elizabeth or below Elizabeth? Well, alphabetically, they both start with E. D comes before L, and so that means I would be in the first half of the list. So I'm going to go ahead and toss out Elizabeth onwards, and I'm just going to focus on Anne and Edward. And of course, there's Edward right there, and so we're done. So it seems pretty complicated. But actually, it's going to turn out this is much faster than linear search. One of the reasons why this seems kind of complicated and you may not be seeing the benefits here is that the benefits are really going to show up as the list size increases. So, if we've got 10,000 items, the binary search is going to make a huge difference. If we've got 5 items, not so much. It just seems sort of complicated, and you're going to be doing all these comparisons, and it just may not seem like you're getting a big benefit. And we're actually going to talk about that a little bit later on, in terms of, well, if you have small amounts of items, the algorithm that you're using, there are different things to think about. Like, is there a big startup cost? And so these are different concerns. So keep in mind when we're talking about analysis of algorithms, we're generally talking about what happens when the numbers get really large, because When the numbers get really large, that's when we can't actually, if we choose the wrong algorithm, we aren't actually able to have a program that actually completes in a reasonable amount of time. So, maybe I can write the program and run on the data set, and in 3 years, it will finish running. Well, that's not a reasonable amount of time. That program is pretty much useless. Okay, so binary search is much faster, particularly as the number of items increases. The number of times we need to search doesn't increase linearly. So we saw that with the linear search. If we double the number of items in the linear search, the amount of time it's going to take to carry out the linear search doubles. If we quintuple the amount of times, the number of items in the list for linear search, the amount of time it's going to take is going to quintuple. Well, what happens with the binary search is it doesn't increase at that linear rate because we keep on splitting the list in half. We split the list in half. We split the list in half. And it turns out that binary search actually increases the log. So you may recall that the way logs work is they're basically determining based on powers. So if I have log 10, that's actually 1. Log of 100 is 2. Because 10 to the second power is 100. Log of 1,000 is 3 because 10 to the third power is 1,000. And log of 10,000 is 4 because if I take 10 to the fourth power, it's 10,000. Now, in computer science, and in particular for binary search, in computer science in general, we often use powers of 2. And then binary search, we definitely use powers of 2 because we are repeatedly splitting the list in half and half and half and half. So I've gone ahead and written the logs base 2 here, and we can write that it was a log with a little subscript 2 there, meaning that we are using base 2 numbers instead of base 10 numbers, and this is also sometimes written as ln of n. But the main thing to note here is that this is much faster. Okay, so we can write the formula for how long it takes like this. Average time to find is equal to constant times log base 2 of the number of items. And again, if you actually work out log of base 2 of the number of items versus just the number of items, and you were to plot the two on a graph, you would see that log of the base 2 is much, much better. And again, I've got that constant there because we are concerned with the particular computer is going to vary in speed. And so what I want to know is, in general, if I'm trying to compare this algorithm to another algorithm, regardless of the specific computer I'm using and how long that computer is going to take, that's where we go ahead and put in that constant. So, I don't know if I have a fast computer or I have a slow computer, but I do know that for binary search, it's going to increase based on the log of the number of items that I'm using. Okay, so log base n is actually pretty good speed improvement. Can I do better? And it actually turns out the answer is yes. And when I first saw this when I was a college student, this blew my mind. I thought this was the greatest thing ever. And so we're going to use a technique called hash tables. And hash tables depends on something called a hash function, which we'll take a look at in a minute. So with a hash table, what we're going to do is we're going to store all the different items that are going to be in our data set in an array. And we're going to give instant access to any item in the array. So, we had to go through each of the individual items using a linear search. With the binary search, we split the items in half, check the upper versus the lower half, split the items in half, check the upper half of the lower half, split the items in half. And if we've got a large list, it's going to be a lot of splits there. It's definitely going to be a lot for the linear search. For the hash tables, we're going to get instant access. You tell me what item you want, and I'll be like, that's exactly where the item is. How do we do this? It's like magic. It's amazing. All right, so as I mentioned, we're going to use something called a hash function. A hash function is going to create an ordinal number from a more complex item. And so our example, we're looking at words in a table, but this technique can be used for other types of data other than just words. Okay, so I'm going to use a simple hash here. This is not necessarily, there's a whole science and mathematics to choosing proper hashes, and I'm not going to get into it. And I have not studied any of this stuff since I was your age, like literally 35 years ago, 40 years ago. It's been a long time. Okay, so we're going to use a simple hash that's easy for everybody to understand. What we're going to do is we are going to form our hash by adding all the ordinal positions of the letters in the word that we are going to place into our data set. Okay, so suppose we have the word cat. C is the third letter, A is the first letter, and T is the 20th letter. And so I'm going to go ahead and form my hash by adding those up together. I'm going to say 3 plus 1 plus 20, because third letter plus first letter plus 20th letter. Add those two together, and I'm going to say our hash function gives us a 24. Now, if we've actually got over 24 slots, then we're good to go. But if we don't have 24 slots, or we've got a limited number of slots where the hash function can come up with larger numbers than the actual number of positions we have, which is pretty common. In fact, in this case with cat, you can make the argument that, well, I can have 26 characters, so it'd be 26 plus 26 plus 26, but that only works if all of our words have 3 letters. So anyway, so it's pretty common to have hash functions come up with numbers that are much larger than the size of the table that you're storing the data in. So what we're going to do is we're going to go ahead and perform a modulus. You may recall that modulus gives me the integer remainder of dividing something out. So what I'm going to do is I'm going to take the hash function, the value returned by the hash function. I'm going to modulus it by the number of slots I have in my table. And that's actually where I'm going to go ahead and look up the item. So in this particular case, suppose we're storing these items in an array which has 10 slots. What we're going to do is I'm going to go ahead and take cat, which gave me the 3 plus 1 plus 20 is 24. And I need that to fit between 0 and 9. And so I'm going to go ahead and take the 24 and do a modulus on 10. And so again, modulus gives me the integer remainder. So this is basically saying, take 24, divide it by 10. That would give you 2 if we were doing integer arithmetic. What's the remainder? The remainder is 4. So the modulus is 4. And so I would go ahead and put cat in the 4th slot in our array here. Okay, so we can do a bunch of these. So dog, D is the 4th letter, O is the 15th letter, and G is the 7th letter. And so I go ahead and add those all together. That gives me 26. I take the modulus, which gives me a 6. So I would go ahead and place cat in slot 4 and dog in slot 6. Tip. And these are just 3-letter words, but you can use whatever length word that you want. That'll get you larger and larger numbers, potentially. But since we're always modulusing by 10, it doesn't really matter. We're always going to end up with a number between 0 and 9 after we've completed that modulus. Okay, so tip. T is the 20th letter, I is the 9th letter, and P is the 16th letter. That gives me 45. Modulus 10, I'm going to go ahead and put that in slot 5. Now, one thing that you may be thinking here is that, hey, isn't it possible to end up with 2 items in the same slot? Absolutely it is. So if I've got cat, that's 3 plus 1 plus 20, and I've got act, that's 1 plus 3 plus 20, those both hash to the same location. And so this is called a collision. And there's a variety of different techniques that can be used to handle collisions, but we're not going to talk about them in this class. If you have a well-chosen hashing function, and if you have a lot of slots, it's not a problem. And it actually turns out, I haven't studied this, but if you study this, it turns out that you can have a surprisingly small hash table and still be pretty efficient. So you might be thinking, well, if I've got 50 items and I have a hash table that's 1,000 items, big enough to store 1,000 items, then I'm not going to have that many collisions. And that is certainly true. But it turns out you don't actually need a table that's all that big in order to not have that many collisions. I'm kind of surprised by that result. Okay, so we've been talking about using the hash to put items in the table. And then, of course, if you're trying to figure out if an item is in the table as opposed to putting an item into the table, you just do the same thing. So suppose I want to look up and see if box is in our table. Well, I go ahead and calculate the hash. B is the second letter, O is the 15th letter, and X is the 24th letter. I add them all up. That gives me 41. 41 minus 10 is 1. And then I check if the item is in this given location. So I say, hey, let's go ahead and check item 1 in our table. Is that box? And if there's nothing there, then I know that box is not in the table. If there's something else in slot 1, well, that's the collision thing that we just talked about a minute ago. And that definitely has some fairly reasonable solutions, but they're a little complicated. So we're not going to describe them in this lecture. Just be aware that, yes, hashing functions can cause collisions where two things hash the same location. That's totally a thing. If you were looking at this going, hey, isn't there something, I seem to recall a joke about dog and God. Won't that create a hash, same hash value? Yes, it will. And there are ways to handle it. Okay. So how does hash tables compare with linear search and binary search? Hash tables are much, much better. It's like I said, it's like magic. This stuff's amazing. So with hash tables, whether my table contains 20 items, 200 items, 200,000 items, it still takes the exact same amount of time to determine the items in the table. I just go ahead and look at the item that I'm trying to look up. I calculate its hash function, which does not change based on the number of items that are in the table, right? Calculating that hash function, it'll take longer if the word's a little bit longer, but in terms of how many data items I have, it doesn't matter how many data items I'm working with. I could have 1 million data items. It's still going to take the same amount of time for me to determine the hash for an individual item. And then I just, it's super easy once you have the hash. You just go to a particular item in the array. That's pretty much instantaneous. So this works super, super well. I think it's pretty amazing. I was amazed when I saw this when I was a college student, which again, probably says quite a bit about me, but I thought it was really, really cool. I was like, wow, this is great. Anyway, so if we want to write a formula for how long it takes to find an item in a hash table, here it is right here. The time to find is just a constant. The exact constant varies, again, depending upon how fast or slow our computer is. So in computer science, we categorize different algorithms using what's called O notation. So using O notation, we would say that linear search is O of n, which essentially means that the time it takes to carry out a linear search increases directly with n, where n is the number of items in the list. Binary search is O of log n, which means that the amount of time to carry out a binary search increases with the logarithm of n. And hash tables are O of 1, which means the amount of time to determine if an item is in a hash table is constant and does not change with n. Let's take a look at the formal definition of O of n. So f of x is O of g of x if there exists constants c and k such that 0 is less than or equal to f of n is less than or equal to c of g of n, where n is greater than k. So the f of x here is the actual performance of our algorithm. So that would be, for example, how much time it actually takes to carry out a binary search. And so the g of x in the case of binary search would be log n. So I would say the performance of binary search is O of log n because the actual performance of binary search, that's the f of x, is less than or equal to log of n times some constant for n is greater than or equal to k. Let's take a look at this c and k business here and see what's going on there. Okay, so 0 is less than or equal to f of n is less than or equal to c of g of n. That's telling us that what we're looking at here is an upper limit. So f of n is the actual performance and g of n is the performance that we're comparing it to. So we know that f of n is less than or equal to c of g of n. And so if we're not able to find the exact performance, but we're able to say, hey, I know this works better than this other algorithm. I know this does better than n squared, or I know this does better than n cubed. That's good enough for O notation. What about that c factor there? Why is it c of g of n instead of just g of n? So that multiplier there, that c multiplier there, tells us that the amount of time it takes to process an individual item is not important. So maybe it takes 30 seconds for one iteration of binary search, and it takes 1 second for each iteration of linear search. And so it turns out that means that for small numbers of n, the linear search is going to be faster. But for large numbers of n, the binary search is ultimately going to be much faster. Let's take a look at how that might work. So again, assuming 30 seconds for an iteration of binary search, 1 second for an iteration of linear search, it turns out that if we have 1,025 items and we take log to the base 2 of 1025, I get 10, approximately 10. So this means that if I have around 1,025 items, on average, I'm going to need to do 10 iterations of our binary search. If it takes 30 seconds for each iteration of our binary search, it's going to take 300 seconds to process all 1,025 items, or to search if I need to go through those 1,025 items. In contrast, I said, linear search only takes 1 second per iteration, but if I have 1,025 items, I'm going to, on average, need to do 500 comparisons, and that's going to take 500 seconds. So what we're seeing here is, sure, for small n, that 30 seconds per iteration on the binary search is going to make a big difference. If I've got 5 items in the list and it takes 30 seconds for an iteration of binary search, even if I only had to do a single iteration, I'm already in trouble. But as n gets larger and larger and larger, the fact that a single iteration takes a lot more time is a lot less important than the total number of iterations I need to do. And so that's what that C factor in there is saying. It's saying, I don't care if there's a constant difference in terms of the amount of time per iteration. I really care about the amount of iterations. All right, what about that n is greater than or equal to k? So what that's talking about is startup time. So again, it's possible for small numbers of items that the initial startup time is going to swamp the actual time in order to process each of the individual items. So let's say it takes a minute for our binary search to get started, whereas a linear search starts automatically. Maybe there's some setup stuff I need to do for the binary search. I need to set up some data structures in order to do the binary search. For small numbers of n, this could mean that the binary search is not the right way to go. But as my numbers get larger and larger, if I'm processing 1,000 items, does that 1 minute startup time make a difference? If I'm processing 10,000 items, does that 1 minute of startup make a difference? If I'm processing 100,000 items, at some point, the better algorithm, the algorithm with the better O notation is going to win out over the algorithm that has a smaller setup time, but ends up having many, many more iterations of processing that it needs to carry out. So that's the basic idea here behind O notation. So what we're saying is, first of all, we're saying that this is a upper end on the performance, that the performance of our algorithm might actually be better than the stated O notation. We'll talk about that in a little bit later. There's some other related notations that tighten that up. I'm saying that it doesn't matter how long it takes on a particular iteration, and I'm saying it doesn't matter how much startup time there is, that ultimately for large numbers of items, the O notation is going to the type of O notation will overwhelm these other factors, regardless of the startup time, regardless of the amount of time in each iteration. Ultimately, the big winner is going to be the number of iterations, and that's what O notation is measuring. Okay, so here are some common O notations here, along with their names. O of 1 is what we refer to as constant. So that's with, like we say with the hash table. Doesn't matter how many times, it doesn't matter how many items I'm processing, it's always going to take the same amount of time. O of log n, that's logarithmic. We saw that with our binary search. Logarithmic is great O notation. So if you've got a algorithm that works on O of log n, that's a good algorithm. O of n, that's linear. O of n log n, that's okay. It's going to kind of depend upon the particular algorithm we're using. So if we're doing a sorting algorithm, O of n log n, that's pretty good. O of n squared, that's quadratic, that's bad. And O of 2 to the n, that's exponential. And that's pretty much like you might as well just give up. That's not going to be able to finish in any reasonable amount of time for any reasonable amount of items. All right, so let's take a look at some related notations. Okay, so we're using O notation, or we've been talking about O notation. That's actually the most common way to talk about these algorithms. And as we've seen, O notation says our algorithm is equal to or better than the given notation. So if I say it's O of n squared, that means it's no worse than n squared, and it might actually be a bit better than n squared. There's also big omega notation, and that means our algorithm is equal to or worse than a given formula. So, if I say something is big omega n squared, that means we know we aren't better than n squared, but we actually might be worse. And then there's big theta notation, which means our algorithm is exactly equal to the given formula. Why do we have these? It's because when we're trying to analyze a particular algorithm, it's not always obvious exactly what the big theta notation is, but we can often find either an upper bound or a lower bound. Also, when we're talking about O notation, typically we're talking about time, but we could also be talking about space. So usually I'm saying as the number of items increases, how much time is this going to take to process? But I might actually be saying as the number of items increases, some algorithms require some extra space in addition to the space actually used to store those items. And so how does that space complexity increase? And in fact, we will find that there's often a time-space trade-off where I can process something quickly, but it requires a lot of space, or I can process something in a small amount of space, but it's going to take a lot more time. Merge sort is an example of something where the time and space complexities change. And so merge sort actually has pretty good time complexity to sort all the items in a list. But it actually turns out, in contrast to most of the sorting algorithms where we can go ahead and sort the items in their original location, so it turns out that merge sort is going to need some additional space in order to sort the individual items. So when considering whether or not to use merge sort, you need to consider both the amount of time it's going to take and the fact that it is going to require some extra space. We should also be concerned with average case versus worst case performance. In general, the most important thing to be concerned with is average case. But if you start worrying about what the worst case performance is, this is useful both, if you want to make absolutely sure that this performance doesn't start dropping off. Well, how's this going to perform in the worst case? It also turns out that analyzing the worst case performance can lead to some tweaks in the algorithm to avoid ever running into that worst case. So probably one of the better examples of this is quicksort. So quicksort is, on average, one of the best sorting algorithms that's out there. On average, it gets us O of n log n performance. However, if the list is already sorted, it actually turns out that the performance of quicksort is actually much worse. It gives us O of n squared performance. And so there's different games that people play in order to ensure that the list that quicksort is using is not, in fact, already sorted. And if it is sorted, they kind of tweak the list around a little bit to make it no longer completely sorted. And that reverts quicksort back to having closer to O of n log n performance. All right, that's it for our analysis of algorithms. Next, we're going to take a look at what are called undecidable problems. I'll talk to you soon.